We're continuing with Chapter 4 in the algebra textbook. In this video, we're going to go through the second section, which is on exponential functions. We're going to be introduced to the exponential function. So let's start by, I want to give you an example of an exponential function. So f of x is equal to, let's say, 2 to the power x. This is an example of an exponential function. We've got some base, some constant base, in this case 2, raised to a power that is variable. The variable is in the power. So let's just start by thinking about how x could be any real number. Yes, we can extend this obviously to complex numbers, but let's start by thinking about x is any real number. Okay, so now we can compare this to, let's say, a polynomial term, x squared or x cubed, or maybe a rational term or a radical term. We can see that the difference is that for these cases, the base is variable. The base can be any number, as opposed to here, it's flipped. The base is constant and the exponent is variable. But what you can notice, though, is that, yes, we have now defined some new type of expression. The exponential is its own type of expression. It's going to have its own name, its own category. In an equation or whatnot, it's going to be distinctly different from terms like this. However, fundamentally from a mathematical standpoint, we haven't defined some sort of brand new operation. These two operations are the same thing. It's just two different perspectives, right? It's just powers. It's a number raised to a power in both cases. Okay, and now, but something else that's really interesting that I want to make sure that you're aware of, and I've been periodically trying to point this out as we've gone through the course. But keep in mind that up to this point, so in every expression we've ever worked with in pre-algebra, the chapter 1, chapter 2, chapter 3, any expression, equation, inequality that we've ever worked with, if you pick out any term in any one of those scenarios, the term is going to be of a form like this. It's going to be some constant times a variable to a rational exponent, where when I say rational exponent, I'm including any positive or negative integer as well. So the term rational includes any one of these exponents. Right? Every single expression or equation or inequality we've ever worked with, all of the terms were of a form like this. This includes constants like 5 times x to the 0, it's just 5. Or just x itself, that's x to the first, right? Okay, and so now in addition to this type of expression or any of these expressions, we're now going to be dealing with a new type of expression, the exponential. But again, even so, the fundamentals of what we're doing from a math standpoint is really, it's just a matter of perspective. We're still just dealing with raising numbers to powers. Now, the only issue with this, if you think about it, the issue with this, there's a problem. The problem is that, so yeah, I mean, we can ignore the potential for this being a complex number at the moment and come back to that later. In a future course. But okay, but with that though, if we think about how x can be any real number on the real number line, okay, well that's fine. So that would include integers, positive or negative integers, that's fine. 0, that's fine. Rational exponents, that's fine. But what about irrational exponents? That's the only case we haven't talked about yet. And if we're going to define a function like this, and we're letting x be any real number, and we want to graph it and analyze it in full, well, then we have to understand how to take a number to any kind of power. And we've talked about all of these cases except for when x is irrational. Like what does 2 to the pi mean? So before we really get into the exponential function and start to analyze the graph, etc., we're going to need to understand what a number to an irrational exponent means. Okay, so now they start off by giving an example of a fundamental example of how an exponential would be used to model something. And what they're saying is that if you imagine you put 2 cents in the bank on the first day of a month, and the deal was that, okay, the amount you have in that account is going to double every day for a month. So you deposit 2 cents, and at the end of day one, it's been there for a day, the amount you have is going to double from 2 cents to 4 cents. And then at the end of day two, the amount is going to double from 4 cents to 8 cents. At the end of day three, from 8 cents to 16 cents. And so you wonder, well, okay, how much is going to be in the account after 30 days? Well, to model this, since this is, we're doubling every day, the idea would be that, so you've got 2 cents you start with, okay, and you want to multiply this by 2 to the power x, where x is the number of days. And so with this, at the end of day one, starting day two, you want to multiply this by 2. So 2 to the first is 2. 2 times 2 is, now you have 4 cents. Okay, but then at the end of day two, you want to double that amount again. And that's going to work out fine because you have 2 cents. You doubled it on the first day. Okay, so, but at the end of the second day, you've got 2 squared. So you're going to have 4 cents, and you're going to multiply that by 2 again. And you'll have 8 cents. And then at the end of the third day, you'll double it again. So this exponential works perfectly. If you want to find out how much money you have at the end of day 30, at the end of the month, you just do 2 to the 30th times 2 cents, and that's $10.7 million. Okay, so that's the idea of an exponential, is that you're multiplying by this common ratio, this common base. Okay, so with that then, let's take a look at the official definition of an exponential function. The official definition. So in general, an exponential function, f of x, is equal to b to the power x, where b is a real number that's greater than 0 and not equal to 1. Okay, now, again, could we think about bases that are potentially some constant complex number? Yes, but that's beyond the scope of this course. In this course, starting out simple, an exponential function is if you got some constant base that it has to be greater than 0 but not equal to 1, raised to the power x, where x is any real number. Any real number. That is an exponential function. You can pick any base you want, as long as it's greater than 0 or not equal to 1, raise it to the power x, that's an exponential function. Okay. So, first of all, why can't the base be negative? What's wrong with that? And I'm saying that because, okay, we could say, what if b was negative 2? Well, I mean, there's nothing wrong with this. We could do negative 2 cubed. You know, you can raise a negative number to an exponent. What's wrong with, so what's the problem? Why can't we do f of x is equal to negative 2 to the x? Okay, the issue with this is that, remember, these different function types that we're putting into their own categories, they're all going to have similar graphs. Okay, that's why the polynomials are separated out into, you know, linear and quadratic, etc., because the graph types are unique. Okay, and so if we think about raising a negative number like this to the power x, and note, I'm not talking about this. This is different, because this is like saying that you've got a function 2 to the x, and now we're putting a negative out front. So no. We're talking about the entire negative number is raised to the power x. The problem with this is that we know that negative numbers, if they're raised to an odd exponent, the result is negative. If they're raised to an even exponent, the result is positive. Okay, but even with that, we have to deal with like decimals and whatnot. So it's going to constantly be changing signs, and then there's going to be cases where you're going to have there's going to be non-real answers. You'll have radicals with a negative number underneath. It's just a big mess. If you go to a graphing software, go to like Desmos and type in -2 to the x power. A graph initially shows up, but there's like holes in it. There's spots that in the negative region, and then if you try and zoom in at all, the graph just disappears. So this is a mess. And if you're going to think about a function with a negative base to a variable power, that's going to require its own separate analysis. Okay, but why can't the base be 1? What's wrong with 1? We can do 1 to the x power. We can raise 1 to a power. Well, okay, for all x, this is just going to be 1, which is a constant function. So this is not, again, these categories are based on, the graphs have the same features. It's the same essence of graph. That's why we had the linear function was its own category, mx plus b, and then the constant function was its own category. It's two kind of different applications, right? And so 1 to the x is a different scenario. And same idea with if the base was 0. 0 to the x, well, okay, x has to be positive. That's fine, but then it's always going to be 0. So that's just like a trivial case. So it's the base is positive, and but not equal to 1. Okay, great. Now, the next thing we need to do before we go any further is, and that's what we're going to do here, is, okay, what about a number raised to an irrational exponent? It says, at this point in the text, we have evaluated exponential expressions with integer exponents and with rational exponents. For example, so yeah, we know what each of these expressions mean. However, how do we evaluate an exponential expression with an irrational exponent, such as 4 to the pi power? So, okay, just to be clear here, let's make sure we're clear here in that we don't understand what this means. That's the issue. It's like when we started with, we knew what 4 squared meant. You're multiplying 4 by itself twice. And then we had to figure out, well, okay, what would something like this mean? And that's what we're trying to do here. We're trying to come up with a definition for what does a number to an irrational exponent mean. So, okay, in such a case, the exponent is a non-terminating, non-repeating decimal. That's exactly what an irrational number means. It's a non-terminating, non-repeating decimal. So it says we define an exponential expression raised to an irrational exponent as a sequence of approximations using rational exponents. So, okay, what they're saying is that this is going to be a little bit hard to understand until you've gone through the sequences and series chapter of calculus. But what they're saying is that you have this sequence here. You can think about a sequence to where we can say that if we're thinking about what 4 to the pi is equal to, then this sequence would be, so we can start with 4 to the 3.14 power. Okay, that's an approximation of pi, just 3.14. Well, in this case, we have a terminating decimal. We can write this as 314 over 100. Okay, we know what this means. This is, so 157 over 50. We know what this means. It's the take 4 to the power 157 and then take the 50th root of that. So your calculator could give you an answer for this. Like this, we know what this means. Okay, so let's see. Let's put this back. That's 4 to the 3.14. And the next term in the sequence would be 4 to the 3.141. And then the next term would be 4 to the 3.1415. And this would continue infinitely because the decimal never terminates. But the key is that each one of these terms in this entire sequence is a number that we understand what it means, because it's a number raised to a rational exponent. And so now how you think about what exactly what 4 to the pi is is you think about it as it's the limit of this sequence. So remember, the limit of a sequence is you're thinking about what's the as the number of terms in the sequence go to infinity, what's the infinite term? And so like the infinite term would still be a rational exponent because we'd stop the decimal at that point, at like the infinite decimal place. It would be a rational exponent. We could write it as a ratio of integers, and we know what that means. We understand a number raised to a rational exponent means from a radical standpoint. Okay, and so now we understand what exactly this means. Okay, but now what is your calculator going to give you if you typed in 4 to the pi? Well, you could just think about it's gonna give you the as accurate of a numerical answer as it can. So it might give you calculate the tenth term in this sequence or something. Okay, great. So now we have the full scope of the exponential function because we can fully interpret a number raised to now any real number exponent. Again, thinking about x as a complex number, we'll talk about that in a separate course. Okay, now the next thing we want to do is we want to get a sense for what the graph of an exponential function looks like and what are its key features. Now, what we're going to see, though, is that in general, all exponential functions, so the different exponential functions are going to be based on whatever you choose the base to be. But the general exponential functions all have a similar type of graph. That's why they're all grouped into this one category of function. However, there are two scenarios where the graphs are different enough that there's two subcategories of exponential functions. So if the base is a number between 0 and 1, something between 0 and 1. It can't be 0, it can't be 1, right? But something between 0 and 1, then we call that exponential decay. And if the base is greater than 1, then we call that exponential growth. And so with that, let's take a look at the graphs of these two exponential functions. We've got 2 to the power x and 1/2 to the power x. So we've got an exponential growth case and an exponential decay case. Okay, so here is 2 to the x, and here is 1/2 to the x. And you can think about how they graphed these by just making a table with an array of different input x values, and then they could use the calculator, input these values into the functions, and put the corresponding outputs. Plot these points and then connect the dots with a curve. Okay, so if we think about where the curve for 2 to the x is coming from, 2 to the power x. Well, okay, if x is equal to 0, then you have 2 to the 0 is equal to 1. And in fact, for any exponential function, since the base is going to be something greater than 0, not equal to 1, I mean, really, you could have any base to the power 0 is going to be 1 except for 0. But no exponential function can have a base 0. So any raw exponential function with no transformations applied to it is going to pass through the y-axis at y is equal to 1. So it's going to have a y-intercept equal to 1. And that's what we see here for both curves. Now, as x increases in the positive direction past 1, so x is going, let's say, from 0 to 1. Well, in that case, we've got like you can think about radicals of 2. When x is equal to 1/3, you've got the cube root of 2, 1/2, the square root of 2, etc. And so when x is between 0 and 1, you're going to have some number that's less than 2, but greater than 1. And that's what we see. And then as x increases, and when it gets to 1, you have 2 to the first is equal to 2. And then as x increases past 1, and in that case, you're now multiplying 2 by itself and then some. So you're going to be getting outputs that are greater than 2. And as you keep increasing x, you're multiplying 2 by itself more and more and more times. So as x goes to infinity, the function just balloons to infinity. Okay, now if starting at x is equal to 0, we go in the negative direction, then what we can think about as happening there is when you have 2 to some negative exponent power, you can write that as 1 over 2 to the positive of that power. And so what's going to happen is as x gets larger and larger in magnitude in the negative direction, you can think about how the function is going to approach 0 from above. But it's never going to get to 0. So it's going to be a horizontal asymptote at y is equal to 0. So, if you had 2 to the negative 1 times 10 to the 50th, well, that's right. So you get 1 over some enormous number is very close to 0, but it's not 0. So you have this horizontal asymptote at y is equal to 0. But what we can see is that an exponential is not going to be able to be negative. There's no exponent you can raise a positive number to and get a negative number, right? Since the definition of an exponential function is that b is going to be positive. Well, there's no real number you can raise b to, positive or negative, and get a negative number, okay? Now, what about 1/2 to the power x? Okay, when x is equal to 0, the function equals 0. Now, in this case, as x increases in the positive direction, you're multiplying 1/2 by itself more and more and more times. That means that the function is decaying towards 0. The more you multiply a number, like a fraction by itself, the number is getting smaller and smaller and smaller and smaller. So in this case, the y is equal to 0 is also a horizontal asymptote, but it's when x is approaching infinity. But as x goes in the negative direction, what happens is you get 1 over 1/2 to some positive power, which ends up being just simplifies to 2 to a positive power. So if you had 1/2 to the power negative 1 times 10 to the 50th, well, you simplify this and you get 2 to the power. And so that's what we see. We see as x goes to negative infinity, an exponential function with a base that's between 0 and 1 goes to positive infinity. And so with that, you can see where the names exponential growth and decay come from. An exponential growth function, as the input increases, the function grows. An exponential decay function, as the input increases, the function decays. Decays towards 0. The exponential growth grows from 0. Exponential decay decays towards 0. Now, one thing we can notice is that if we flip an exponential function, so 2 to the x, if we flip this about the y-axis, so we put a minus in front of the x, well, the result is that what we get, which is right, and vice versa. So if you flip an exponential growth curve about the y-axis, you get the corresponding exponential decay curve with the same rate, the same like equivalent bases you can think about, and vice versa, right? If we flip this about the y-axis, we'd come back to 2 to the x. Okay, and so with that, we can summarize the graphs of exponential functions. So any exponential function, a growth or decay function, is going to have domain all real numbers. You can input any x value you want, and you're going to get an output, right? Because the base can't be 0 by the definition, so you can input any x you want. So the domain is all real numbers. And we saw that the range is 0 to infinity, not including 0. Okay? We saw that so there's no x-intercepts, obviously, and we saw that for any exponential function, the y-intercept, in all cases, for an untransformed exponential, is at y is equal to 1. Okay, we saw that y is equal to 0 is a horizontal asymptote for any exponential function. But the only nuance being that if it's an exponential growth function, then it's going to approach the y is equal to 0 as x goes to negative infinity. But if it's an exponential decay function, it's going to approach y is equal to 0 as x goes to positive infinity. Okay, now here we compare exponential functions with two separate bases, but more specifically from the standpoint of the bases are both greater than 1. So we're trying to get a sense for the effect of just a larger base on like an exponential growth curve or an exponential decay curve. But in this case, we're looking at exponential growth. So here they graph 5 to the x and 2 to the x. And so what's going to happen is it's just going to grow. If you have a larger base with an exponential growth case, it's going to grow. The larger base is going to result in a faster growth. That's it. And then, but when you're going in the other direction, so it's when with a positive or a base greater than 1 function, it's like it is decaying towards 0 in the negative direction. It's going to decay faster as well. So you can see here, 5 to the x grows faster than 2 to the x, but it also decays towards 0 faster than 2 to the x. And we can think about if we had for the case of exponential decay, the smaller the base, then the faster the decay is going to be. So if you had, 1/2 to the x and 1/8 to the x, then they both cross at y is equal to 1, the y-axis, but then 1/2 to the x is going to do something like this. 1/8 to the x is going to do something like this. And then similarly, 1/8 to the x is going to balloon in the negative direction faster than 1/2 to the x. Okay. And now the next thing they talk about is transformations applied to exponentials, but this is really straightforward. It's all the same rules. So if we had f of x is equal to 3 to the power x minus 2 plus 4, well, this is just going to be shifted to the left 2 units and up 4 units. It's going to be 3 to the power x shifted to the left 2 and up 4. So the new asymptote axis is going to be y is equal to 4. And like the new y-intercept is going to be what? So instead of 0, 1, it's going to be 2, 5. It's been shifted to the right 2. I think I said left, to the right 2 units in the positive direction.